So those were about the logistics. So assignment 2 is due next week. And it's a very simple recommendation system. So hopefully you'll see much more interesting recommendation systems. In fact, some of them use just feed-forward neural networks, for example. And that's the area where I work in. So, happy to chat with folks offline if you want to delve deeper into recommendation systems. But let me get back to where we are in our journey. So what we've done so far is we motivated and did a review of typical classification setting, because many of the techniques that we're seeing so far are mostly related to supervised learning. Okay, so we do have supervisory signal, either the label or the class of the image or some other object like that, right? So we started with thinking of the prototypical supervised learning setting, a classification problem, and then talked about back propagation. Then we started looking at three different, I guess, neural network architecture / components. In the second lecture, we saw feed-forward neural networks and got started on convolutional neural networks. And in the third lecture, we kind of spent a lot of time on not just CNNs, but once you've trained a CNN, there are a few ways to kind of understand whether it's working well or not, like occlusion-based or using projection, projection of the data points to see if the projected points are clustered in the two-dimensional space or not, right? And then we looked at a few things like batch normalization, dropout, and so on. Okay. In the last lecture, in the two lectures before that, we saw embeddings. Okay, so we switched from images to text, and we talked about we talked about some NLP models like naive-Bayes classifier. I guess the new model there was, for example, latent digital allocation, right? So that was new, but it was not. But all these models were not exploiting semantic similarities between words, and so we defined, hey, this is how we would think semantic similarity should be captured. That is, we want to get vector representations of words where words which appear in similar contexts have similar vectors. Okay, similar in terms of like inner product or some sort of like a Euclidean distance, whatever you want to call. Okay, so that led to the idea of word2vec, which we covered at the beginning part of last lecture. It's basically an auxiliary task which was trained on a large English text corpus initially, about 8 to 10 years ago. And the outcome of that training process, that supervised learning, was getting these, for example, 300-dimensional vectors for each word in our vocabulary. Okay, and now since then there are so many other implementations, not just for English but also for other languages, that you can choose to use, for example, in assignment 3. Okay, so that's what we saw at early part of last lecture, and then we started talking about another model, another family of neural network models, which take into account sequences as inputs and sequences outputs. Okay, so the canonical model there is the recurrent neural network, and we saw how the building block of the recurrent neural network, it can have a simple internal wiring where there's only one tangent layer, linear layer basically, with a tangent nonlinearity, or it could have a little bit more elaborate setup inside, which is what we saw with LSTMs. With that, what we're going to do today is come back to what are some example sequence applications and see how LSTMs are used there. Okay. And then we will, today's scope is to kind of round up, and this is kind of the roundup and try to reach some of the more latest generation models which work with text. Okay, so the names of the models, for example, you can just call them the family of transformer-based models. And so we'll try to get to that. Okay, so one example, famous example, is called BERT. We'll expand the acronym later, but today we want to kind of look at these newer architectures. Okay, so it really, we are actually looking at one architecture kind of per lecture. So it's a lot of new information. But at the same time, I'm hoping it becomes easier to kind of understand the forward pass in each of these architectures, because once you understand the forward pass, the gradient descent and optimization of the parameters of the models is kind of similar across the board. Okay, I hope the context is clear. So just to give you a little bit more details for like what the goals of today's lecture are. So yeah, so today we're gonna round up on some applications of sequence setting. Okay, so where, for example, things like RNN and LSTMs can be used, and in fact, those same applications are applicable for the models that we're going to discuss today as well. Okay, so which is transformer-based models, and the goals for today are three. First is to understand what is called self-attention. Okay, so we're going to look at, it's a core component of the transformer model. So we want to understand what is self-attention and how does it differ to a slightly different form of attention, which is used for LSTM situation. So which is used with LSTM models. Okay, and we're gonna spend considerable time on both of them. So hopefully by the end of the lecture, we'll understand, hey, there is this LSTM style attention mechanism, and there is a self-attention mechanism. Okay, so I'm calling it mechanisms, but at the end of the day, they're just some connections, some neuronal connections. At the end of the day, it's just a function definition. Okay, just like each linear layer, each convoluted layer is just a function definition. Take some input and produces some output. Okay, so attention mechanism or attention is also just implemented as a function. Okay, take some input and produces some output. So we want to understand these two slightly different, but at least conceptually they want to achieve the same thing. So these attention mechanisms, and then transformers have a particular vocabulary. In particular, they have notion of keys. They have a notion of values, and they have a notion of queries. So they are just vocabulary. These are just some ingredients while defining the transformer architecture. And we want to understand how they work, okay, what they are and how they work. And then towards the end, if not today, maybe next lecture, we're going to try to look at an implementation of this transformer idea, which is called BERT, and look at its key characteristics. And there's an example in the slide deck which kind of shows how to use this transformer architecture as a pre-trained model for general NLP tasks like sentiment classification. Okay, very similar to how we could use a pre-trained CNN, and in fact, you are using a pre-trained CNN in assignment 2, right? Like ResNet 18. So it's very similar to that. We're going to use a pre-trained model, which is BERT, to for a particular NLP task, but it can generally be used for other tasks as well. Okay, and I'll also contrast with word embeddings that we used. They are also actually pre-trained embeddings, which can be used elsewhere, right? So we'll briefly mention that. Those are the three key goals for today. Okay. So if you have any questions or comments, at least on the overall setup of where the course is finished and where are we going next, please use the chat or use the mic. What I'll do is now resume where we left off last time. Okay. So let's see. So let me know if the presentation mode doesn't work, then I can just switch back. Are you guys able to see do you still see the nav bar and all that at the top of the browser, or?
No, we see the today's outline.
Okay, so you see just the slide, right? Not the extra information.
No, just the one.
Okay, that's great. Thanks. So this is, let's see, which slide is this? Yeah, so this is slide 55, I guess. Yeah, slide 54 onwards, okay, from lecture 5. So what we did in lecture 5 was cover recurrent neural networks, talk about persistence, and then looked at a specific specific implementation variant, called long short-term memory, okay, LSTM cell. Okay, so the cell inside the RNN architecture. Okay, and we also briefly mentioned as, hey, there are many other variants. One of them is called GRU, I think. So there are definitions that you can see, for example, on PyTorch's documentation, right? So now what we're going to do is step back and now talk about applications, because how to use RNNs may slightly change based on the sequence input, sequence output setting. Okay, so let's actually talk about an example that we have seen a couple of times before, which is sentence classification. You can also call it sentiment analysis, and there are many other names. So basically, the input is a sequence. The output is a single class. Okay, so you just need to. So the output is not variable length, where the input is. The sentence can be of length 3 or length 5, and so on. Okay, so we saw how to use a CNN for this task when we're talking about embeddings, or when we're talking about in the slide deck which had word embeddings, right? So how to use an RNN in this situation. And this, by the way, should give you a sense that, hey, we can do any time series model, not just sentence classification, which is you have a input, which is x0 to xt. So the time series length, I'm calling it time series, but it's just a sequence. Okay, so sentences, in fact, can be variable length. Whereas if you think of a time series setting, you may have a fixed length of, hey, I want to look at the previous x data points to previous 10 data points to predict the next data point. Okay, so here, this is how you would use an RNN for this time series type of problem. Okay, so you pass the input, first input, you kind of ignore the first output, take the hidden vector, pass that vector to the second call to the RNN cell, and pass the second input, and so on. And then what you do is you discard the final. So the final output generally is the same as the hidden vector. You take that, and you may have to do one more transformation to it, because this vector maybe is a vector of length 10, and maybe you're doing a 2-class classification. Then you need to have an extra a linear layer, basically, so that it comes down to 2 scores instead of 10 length vector. Okay. So that's how you would use an RNN for a typical sequence input and a fixed length or a fixed output, like a classification setting. Okay. Or it could be regression, but all I'm saying is the output is fixed. We don't care about, we are not producing a sequence output at the output side. Okay. Now here's a problem which is slightly different, and in the sense that it flips the order. Here, the input is a fixed size, typically, that's a fixed size, which is an image, and the output is a caption for that image. So the caption can have 2 words, 3 words, or 10 words. Okay, so you can see in this diagram that we're going to use an image as an input, but image directly, it's unclear how to pass it as input to an RNN. Of course, you can vectorize it and all that, but the way we're going to do it is actually pass the image to a pre-trained CNN, typically, and then you get an image embedding, and that embedding is the one which kind of starts is the starting point for the RNN to start generating the caption. Okay. Now you may say, hey, what are the how do you deal with generating a variable length output? And that's the important aspect to this example. So let's look at that. So in fact, we'll open up these 2 blocks. So we'll start with test image, pass through a CNN model. For example, on the left side, you see the BGG16 model. Typically, you will drop the last output layer or one more layer before that. And then what you do is RNN operation to generate the caption. Okay. So how do you generate the caption? You're gonna, so we are only thinking of the forward pass, by the way, just keep that in the back of my mind. We are not doing gradient descent. Okay, so gradient descent requires images and caption pairs, and then you'll somehow compute the loss and do the gradient operation like that. But first, before we talk about losses and training data and gradient descent, let's talk about if you had a model, okay, which does captioning, how would it work? So you start an image, pass through a CNN, potentially pre-trained, you get a vector, and then what you do is slightly change the RNN so that it takes this vector as an input while generating the first output. Okay, so what do you do? So you start with a fixed word at the beginning. Okay, so the fixed word here is actually, it's not really a word, it's a token. It's called start. Okay, so start will have a vector. And so you pass that vector as an input to the RNN cell, and you also pass the image embedding as an input. Okay, so the image embedding gets multiplied with a weight matrix, okay, which will need to be learned, and then that is an additional input for the first cell of the RNN. So it's just an extra input to the RNN cell. So remember, if we were concatenating the input with the hidden vector. So, and then multiplying with a weight matrix, or it's the same as doing this. So instead of that, we just have an extra linear transformation for the image embedding that we get. Okay, and then think of, let's for simplicity think of not an LSTM block, but a regular the vanilla RNN block. Then it will just be, do a concatenation, multiply with a matrix, and then do a tanh operation, and that's your H. Okay, the hidden state or the hidden vector. Okay, that's H naught here. And then because you need to produce a word, this H naught has to be transformed to a bunch of scores. How many scores will we produce? The number of scores will be the size of the vocabulary. Okay, plus maybe an extra word, couple of extra keywords like end or something like that. Okay, so you produce scores, and then from there you get a bunch of scores. Maybe one of the coordinates is the highest score, one of the words has a high score, then that's, for example, a likely word for the first word for your caption. Or because you have all these scores, you can certainly get the probabilities. You can actually sample from there, okay, from these probabilities. It's a probability mass function over the vocabulary. You sample from there, and maybe that sample yielded a word called straw. Okay, so the sample yielded a word called straw. So that's your first word of your caption. Then what you do is you also take that word as an input for the second step of your RNN, second step of your RNN model, which is that you got straw as an output, for example. You take that as the input, and then pass it along with the hidden vector that you produce at the first step. These two, again, it's the usual operation: concatenate the two things, multiply with the linear matrix, matrix, the tanh operation, and then again produce a distribution over your vocabulary. Okay, and maybe it produces some word hat, and then you again repeat the RNN operation. You get an output, and you hope that maybe the scores are such that maybe there's the special token I was saying. Maybe the end token has the highest probability, and so you stop there. Okay, so then you get start, straw hat, end. Okay, for example, that's the caption. Let's say it's an example caption for this image. Okay, that's how the forward pass would work if you have maybe the trained model. Any questions about this? So just to kind of step back, this is a fixed input, like an image or a fixed vector. But what it's producing is a variable length output. Okay, so to produce variable length output, you produce one thing at a time. So you produce the first word, then you produce the second word, and then you produce the third word. To produce the second word, you kind of rely on what was the first word, and also the previous hidden vector that you computed. Okay, so instead of exogenously providing the second input, third input, and so on, which you don't have when you're decoding on the output side, you're going to use the previously generated outputs as inputs for the next step. Okay, so that is actually, in fact, the core for the next couple of examples that we'll see, which is this idea of producing a variable length output, right? So here's another example. We want to produce, here's, I guess, another example in the sense that now we are saying, hey, on the input side also, instead of an image, which is a fixed length input, let's make it variable length. And here's an example for that. Translation, summarization, speech transcription, question answering, they will have variable length inputs and variable length outputs. We already saw how to process variable length inputs. It was an RNN, right? So we should just pass each word of your sentence, for example, and whatever is the length of the sentence, that many times the RNN block or cell is called. And then on the output side, we also saw with image captioning that the RNN cell will not the same RNN cell, maybe a different RNN cell, but it will be called, let's say 5 times, 6 times, however length, however would be the length of your output. Okay. So auto reply is one where you get a text as an input, like an email, and it will have variable number of words. And then from there, so that will be processed via an RNN computation, like several times, depending on the length of the text. And then a decoding procedure, or basically there'll be a step where you are trying to produce a variable length output. And that happens very similar to how we did it for image caption. So here auto reply is just at the bottom, you can see 3 different replies. And we'll talk about that nuance in a second. So you can see that given this text input, we're producing a 3 length output, which is count as in. We're also producing some other examples like, sorry, we won't be able to make it, and so on. Okay. So that's an example of variable length output, variable length input, and variable length output.
Professor,
yeah.
Does it make a difference if you use LSTM or CNN for this model, like for this type of application?
So here it's unclear how to use CNN, right? So we need an LSTM/RNN architecture here because the length of the input and outputs are variable lengths, right? Which is not the case here. Here the input is a fixed size image, okay? Or you crop the image so that it's a fixed size always. So that input is not variable length. Input is a fixed size length, okay? 200 or 30 cross 32 cross 3, for example, like say FAR10. Output is variable, which is hey, it could be a caption with 2 words, or it could be caption with 10 words. This example, we are saying that, we want to talk about the architecture when the input and outputs are variable lengths. And so CNNs don't make sense at the moment. Okay. You can use a CNN idea for sentence classification that we have from word embedding slide deck if you want, but that will only address the input side. Okay. But
So
that's
for this one is
CNN
sorry. For this one is an RNN actually.
What's it?
For this model.
Yeah.
It's not CNN. So what is it exactly?
Yeah, so we'll see the architecture in the next slide, but it's going to be just RNN. So we just saw, so this is an RNN, right? So H0, H1, H2 are produced by the RNN cell. We saw the cells last time, right? LSTM cell or the vanilla RNN cell, right? Similarly, in the previous sentence classification example, we saw these are just RNN cells, right? Which were able to process variable length input. Here, the RNN cells are able to process variable length outputs. Okay, so now we have a problem which has variable length input and variable length output. We're going to still use RNN cells. Okay, in fact, here's the actual diagram. Here's the first example. Okay, so there are many architectures here, but let's start with the simplest version that we can by stitching together the sentence classification part and the image captioning part. Okay, so you can see that, let's say I have a very, so we are only talking about forward pass, by the way. We are not talking about training and all that. So here's a example sentence pair, right? So I'm saying, hey, hi, how are you? Is the, let's say, the email or whatever chat message, and then you want to respond, okay, I'm fine, thanks, right? So because this input is variable length, you are exactly going to do what you did with sentence classification. So you're going to pass hi first, create a hidden vector, you ignore the output, and the hidden vector plus the second word together will pass to the RNN cell, produce another hidden vector, and so on. So you can produce all the way till the length of the sentence. Let's say there's a special token which says, hey, here's the end of the sentence. Once you get to the last word of the sentence, then that output you're gonna give as input for a decoding step, which is very similar to the image captioning thing. Okay, so instead of passing the image embedding, we're passing the hidden vector after we processed all of the input. Okay, and then from there, and then given the end word, I'll start producing the first response. Okay, let's say I'm producing I am. Okay, so how is I am getting from here? So hidden vector, we have to map it to the vocabulary size output vector. Okay, scores vector, right? So that scores vector could be the length of the vocabulary. So that's why there's a W matrix here. So going from hidden vector to the scores from which you can get the first word, or so most likely word or a sample. And then in this version, what we're showing is actually even worse than that, in the sense that then what's happening is we are directly trying to generate the second word and third word and so on without looking at the first one. So what we did in image captioning is this, okay, which is we generate the first word and then pass the first word in addition to some transformation of the previous hidden vector as the input, and then that produces the second word. That second word is passed in along with the previous hidden vector as together. So this G1, and then that produces the second word, and so on. Okay. So this part you can see in the red is exactly the same as the image captioning's decoding, okay, or image captioning's output creation of the output sequence. And the white part is exactly the same as the sentence classification's input sequence processing. Okay, so you stitch them together, and the white part you call as an encoder, and the red part you call as a decoder. Okay, so this is a typical encoder-decoder architecture that you would define to deal with variable length inputs and variable length outputs. Okay, so this is the architecture. So for you just asked the question, right? So what is the architecture which relies on RNN? This is how you create an architecture. So any questions about this part? Yeah.
So in RNNs, we do have a fixed architecture, right?
No. So this is the architecture which changes, the diagram changes depending on the input length and output length. So what is fixed is of course, this building block, whether it's the vanilla RNN cell or whether it's an LSTM cell, it will have its parameters, right? The weights and biases of the Danish, corresponding Danish layer, or in LSTM, there are many more other weights. But, but the length here, the architecture diagram just depends on what is the sentence, or what is the input output pair you're looking at.
Yeah, got it. Thanks.
So there's a bunch of parameters on the white cells, but they're all the same, in the sense that it's the same cell being used depending on the input length. Similarly, the red ones, it's all the same parameters. It's just being reused depending on how much output length we can generate. Okay, so as I said in the image captioning part, you wait till you get like something like an end token or something like that, which says, hey, this is the end. You should not generate more output words. Yeah.
So do we say that RNNs are self-adaptive?
No, they're not adaptive, right? So the whole point is we wanted to work with sequence input, sequence output settings, which is a little bit non-standard supervised learning setting, right? If you recall the beginning of the slide deck, we showed, actually, let me be on slide 67. Let me just go back to slide 2. Yeah, so if you think of, this was the typical supervised learning you've been seeing so far, even CNNs, right? So the image was an input and some class was an output typically, right? The moment you want to generate multiple outputs, you have to use, these RNN blocks, right? So we don't use the word self-adaptive, Zoeb, if you're asking that, because, we are, so irrespective of whether we're generating 3 outputs or 5 outputs, it's the same parameters. Okay, same cell being reused multiple times. For example, in the second image captioning situation, in the sentence classification situation, it's the same cell being used to get to one class.
I get it. Yeah.
And of course, you learn the parameters. There's a training part which we are not really discussing too much. And so this example that we saw just now, which is the image, what is it called? Auto reply. So first part would be here, all the RNN cells are being shown the same color, but just think of the first part being the encoder up to maybe this one. And then there's the second part, which is the decoder cells. Okay, so which are producing the output sentence.
Got it.
Yeah, so a minor point, which is at the below this, the last point, the point that you can see in the slide is just saying that at training time, what you do is, irrespective of what you produce as the output sentence, you actually input the sentence that you have as in your training. So in your training, you should generally have, hey, here's the input email, here's what you should respond. So instead of passing whatever you generated as an input, you actually, the reference response you should be generating for that input, because your supervised training has that information. So you instead use that training data itself as input. Okay? You ignore the you do the usual cross entropy laws that this word, the right word is whether its score is high or not. But in addition to that, you actually pick the right word to pass to the next decoding step and so on. Okay, so it's a slight, I guess, minor point about the training portion. And you'll see this example is exactly what you will have to work with in assignment 3 when you do language translation. So we'll come back to this type of a setup again in a few more slides. Okay. In fact, next we'll talk about how to decode better, right? So in the sense that you can see that, let's say we're looking at decoding it this way, right? In the sense that, given the one hidden vector from the after processing all the inputs, we start with the first decoded word. Okay, so let's say it's I am. Then I'm just taking I am and then passing it as input to the next step, and then I'm getting a word fine, then passing fine in and getting thanks and so on. But there is a risk. Okay, there's a risk with doing that, which is that like how did I get I am fine, thanks, right? So I got some I got some hidden vector input and the current I got I'm here and then some hidden vector input, and then I produced the word fine, right? So that's the word fine. And typically what would be the word fine? Either you sample or you pick the highest probability, okay? But the problem is with each one of them, it's a little bit too constrained. You may be making a mistake in the sense that you may be choosing a suboptimal word, and then that will influence all the downstream things you will do, right? If you pick a word which is not the best word to pick at that location for the response, then because that word is what's going to feed into the next decoding step and so on, you may be completely going the wrong way, suboptimal path. Okay, suboptimal sentence may be getting constructed. Okay, so just using one word and then moving forward is what is called greedy, and so it doesn't correct for potentially mistakes I can make early on. So if I make a mistake instead of I say something completely unrelated like university, right? Then that's not probably, and if I use university as an input next time, then it's going to completely bias and give me a wrong response, right? So to deal with that, there's this notion of what is called beam search decoding. Okay, it's a really old idea. Okay, so it's been there. It predates, I guess, deep learning, a recent deep learning, work from the last decade. And the idea is as follows, right? So generally, the way you decode, right, in the decoding step, is you start with an input, right? So you get the hidden vector from the encoding side. You say, hey, start decoding, and then you produce the first word. Instead of producing only one word, which could be the highest score or maybe a sample, you actually, for example, you can do like top 3 words, okay, or the top 3 samples, okay. And then in the next step, you pass all the 3 words and try to get, hey, for each word, what is the top 3? Okay, top 3 next words that you can get. So you're actually doing decoding, not just relying on, let's say, only one of them. So for example, in the previous this decoded sentence is just one path. Okay, one path, like maybe from here to here to here. It's just one path in this decoding procedure. Okay, so you just keep track of what are all the possible sentences or whatever the possible output sequences you can get, but no, you cannot keep track of all of them because that will be too many, right? So if you given input, you will have a full distribution over the full vocabulary, and if you think of each word as a starting point, you can have, for each word there could be another full distribution, full vocabulary. That's too much to take care of. But you take the top 3 or top 5 and so on. So that way, at least you'll have a bunch of candidate captions or bunch of candidate responses, and then you can again evaluate, hey, which of the sentences is the better one to report as an output. Okay, how do you do that? So you can actually keep track of not just the word, but also with what was its probability or score. And so you can actually get a sense of maybe score for the high word was high, but then everything else that followed, the scores were low. Then the aggregate score for this whole part of the decoding, these decoded sentences would be low, whereas maybe the score for yes was moderate, but sure was also moderate, and maybe end was moderate. Then maybe that's the right sentence to pick. Okay, so you can keep track of, instead of being greedy, as in like only going down one decoded sentence or sequence, you kind of keep track of a few. Okay, that's called beam search decoding. Okay, so let's actually fix another issue, and I'm going to switch to a different slide deck in a second, which is that if you look at this encoder-decoder architecture, you see these white boxes, which is the RNN cell being called several times. The only thing that is being used to decode is actually just the last hidden vector, right? So it's as if the whole sentence somehow has to be captured in a bunch of numbers, which are the coordinates of this last hidden vector. Okay, so whether the input sentence is like has 5 words or 500 words, all that information somehow has to be present in that vector, and only then I can decode my response, right? So there's a way to fix this. It's called the attention mechanism. Okay, and we will look at the attention mechanism using a slide deck, which is I guess which has a suffix 5a, the fifth slide deck, and has a suffix a. So we'll look at the attention mechanism fix to deal with the fact that we should not rely on only the last hidden vector to kind of decode. Okay, so that seems like a bad idea because there's a lot of hidden vectors, a lot of information, but they may all be like lost if you're only looking at the last hidden vector. So I will Yeah. So I'll talk about the attention in a couple of minutes. Let's look at one more example, just to see one other example of a sequence setting, which is speech transcription. So you're going from voice, which is a time series, like sound, right? It's a time series. If you think of a measurement like a mic picking up the sound, so there is some analog information which you can digitize it, and then somehow you're at the end of it, you're getting a finally either a sentence in some language, or you're actually getting again it's translated to some other language and then converted back to a sound. Okay, so traditionally what people do is build they used to build separate modeling components. Okay, so for example, there used to be something called an acoustic model, which is given the word, how does it sound? Okay, given a word, what should the sound waveform look like? Okay, and there's also language model. We have seen language models. Given previous words, what could be the next word? That type of a model. And then a bunch of feature engineering to build a speech transcription overall solution. Okay? But instead of doing all this traditional stuff, what you can do is exactly the same as before, like sequence models using RNNs. Okay, which is again you pass as an input a bunch of vectors which correspond to the input sound, and then you can get back as an output a bunch of words, or you can actually get back sound from a different language. Okay? So how does the vectors for the input side look like for sound? Really, sound is like this, right? So you can see the waveform here. So it's just a bunch of, think of time series, it's just a bunch of sinusoids, okay, collection, in fact, a mixture of sinusoids. Okay, so like this maybe corresponds to the sentence, hi, how are you? Hi, how's it? Right. So what you do is actually take this analog waveform, like a signal, right, one-dimensional signal. You convert it into vectors. Okay, because if you remember the RNN, we have to give x0, x1, x2, x3 up to some variable length, right? So we convert this to vectors using a pre-processing step. We'll not discuss the pre-processing step, but it's a way it uses some signal processing ideas to get to vectors. Okay, and you can see the first vector may correspond to one part of the signal, the second vector may correspond to another part of the signal, and so on. So you can see a lot of green boxes, and they're also overlapping. Okay, so when you create this vector for the second, let's say, input, it'll have an overlap part of the input sinusoid, or not sinusoid, sorry, input waveform, and the next part will also have an overlap with the previous input. So the same inputs are being fed into both the first to produce the first vector, second vector, and so on. So that's why you're seeing a lot of overlapped green boxes. But if you think of it, it's just a green box for one part, green box for another part, green box for another part, each one creating a vector. So that's how you generate it. In this figure, I'm just showing you a more elaborate diagram where it's not just RNN at one layer. We just saw an example where RNNs can also be at the level of 2 layers, right? Or 2 levels, sorry. And you can do something like this. So you can go from sinusoid to vectors to an RNN encoder part, and then given the encoder part, you can start decoding. Again, decoder has potentially like multiple levels. Okay, so this is an example of that. Any questions here? What we skipped is did not skip, but what we have to talk about is dealing with the fact that, hey, I'm computing all this information and I'm only producing the last vector, and that's the only one which is being used for decoding. We'll try to change that, and that's using an attention mechanism. Okay? So we'll talk about that, but I wanted to kind of check if at least examples make sense, right? Why it's not the same as regular supervised learning, because the input-output lengths are arbitrary. Yeah.
This is the LSTM, right?
Yeah, so there's white cells, the squares that you're seeing, that could be an LSTM cell or a GRU cell or a regular RNN cell.
When we are going to use a GRU and LSTM, do we have any?
It's just as simple as just calling nn.lstm versus nn.gru if you're using PyTorch. Okay. When one is better than the other, you just have to try empirically. Okay. So the ones in Python, the ones in PyTorch documentation, the ones implemented are kind of the popular architectures, right? The popular cell definitions, and that's why they are there. not, it's not expected that one is uniformly better than the other, as in like it completely dominates the other. And that's why you have those three definitions, especially, for example, in PyTorch. Same is true even in TensorFlow, right? So a priori, it's not clear. Yeah.
Okay. Professor, when you just said that the length of a vocabulary, what actually does that mean? Is the number of words, or
yes,
it's a number which model automatically generate?
No. So think of the output, right? So if you have a hidden vector, let's say is of dimension, let's say 300 for simplicity. Hn or h1, all of these are 300. Even g0, g1, let's say is 300. Your vocabulary, it's vocabulary of the English corpus may have 50,000 words. Okay, then you have to go from the 300 dimension vector to 50,000 scores, because you have to say which word is what, you want to say, you want to pick a word, right? So that's fixed. The vocabulary size is fixed. You just need to produce. Yeah.
Then there will be a matrix of 50,000 cross 50,000, right?
No, you need to go from 300 to 50,000. So think of it as, it's very similar to what ants versus bees versus Cifartan are doing, right? If ants versus bees, the ResNet was connected to two output scores. In Cifartan, it's producing 10 output scores. If you want to have 50,000 output scores, it will just change the final W matrix.
Okay.
Yeah, it's just a change in the output layer. Yeah.
Thank you.
Okay, so let's actually talk about attention. And it's exactly in the context of our encoding decoding setup. Okay, so let's look at attention. So attention, we'll describe what is the computation that's happening, and then kind of give intuition of why that makes sense. Okay, so remember the problem is, if you think of the encoding steps, only the last hidden vector was being used in my previous couple of slides, right? We're trying to fix that. Okay, so that was the problem. Don't just use the last hidden vector to produce the next, the decoded output. Maybe use more information. And how do you use that more information? Here's one proposal. Okay, the proposal is, hey, let's say you're doing language translation in this bunch of slides. We're just going from French to English. Okay, so we'll start with the first, let's say the 4 words here produce 4 hidden vectors. So think of these 4 dots as one hidden vector. These 4 dots is one hidden vector. These 4 dots is one hidden vector, and these 4 dots is one hidden vector. So the 4 hidden vectors that were produced. Okay, because the input length is 4. Then what we do is, we're going to now start the decoding step. Remember, let's say we're doing language translation, so we're going to start the decoding step. To start the decoding step, we take the last output here and take, let's say, some starting token, so some indication to say, hey, now let's start decoding, and produce one hidden vector, right? So this is, again, remember, this is a decoder side RNN cell, got 2 inputs and is producing a hidden vector. Okay, and that hidden vector, we're going to call it S1. And these original input hidden vectors, let's call it H1, H2, H3, H4. Okay, and this one is S1. So what we're going to do is now start some extra computation, okay, which we did not see before. So that extra computation is that we're going to use H1 and S1 together to produce one number. Okay, that's represented here in the blue dot. Okay, so that number is called an attention score. It's here we're representing as A subscript 11. Just to show that, hey, A11 was produced using the first hidden vector on the encoder side and the first hidden vector on the decoder side. Okay, that's why it's 11 here. So this function f, we're going to talk about it later. Okay, so there's some fixed function. So that's attention score for the first input on the encoder side. Okay. Now, why we're calling it attention is because this score is somehow saying that maybe this first input, how important is it to produce my first output? Okay, so that's what we're going towards. We want to kind of say, hey, don't just use the last hidden vector. Let's talk about, hey, while producing any output at the decoder side, is any other hidden vector, is any other input important? Okay, any of the previously seen inputs, in which one is important? Okay, so let's at least mechanically understand how attention scores are produced first, and then add intuition. Okay, so first attention score we produce like this. Similarly, the second attention score we can produce very similar ways. Take the second hidden vector, take the same hidden vector we produced on the decoder side, the first one, as S1, and then let's call it A12. Okay, so the first index corresponds to, hey, we are trying to decode, we are using the first decoder's output. And second index corresponds to encoder side's hidden index, okay, hidden vectors index. Similarly, A3 and A4. Okay. So there are 4 numbers that we computed. The only thing that changed is that there's a function already. The only thing that changed is the inputs. We passed each of the 4 inputs, hidden vector inputs, and we use the fixed decoder's hidden state as well, okay, to produce 4 numbers. Now what we'll do is actually normalize them. Okay, so whatever the numbers were, we're gonna apply softmax operation. So it's exactly the same as what we're doing with the output scores, right? So it's e to the power, each number divided by the sum of e to the power all those numbers. Okay, so just normalize them between. It should look like a probability mass function. Okay, the PMF. Then what we do is take a so actually before that, let me explain. So we got this normalized numbers. Okay, so what does this normalized numbers mean? We're trying to say that, hey, we produce these attention scores. We actually want to just start producing output, right? So we want to start producing output, which means we want to start producing, let's say, the first translated word. Okay, the intention is that while trying to produce the first translated word, maybe the first word of the encoder, the first word that passed through the encoder is actually more important. Okay, so you can see that these normalized attention scores are basically this attention vector. This one seems to be the highest compared to these other 3. Okay, it's kind of an indication that maybe while I'm producing the first word, this first index of the hidden vector is actually important. Okay, important in the sense that vector may inform me in better producing the first one. So in the sense that if I can somehow, since it says that, hey, maybe the first hidden vector is useful, then maybe I can use that information while producing the first word at the output. Okay, so how do we use that information? We're going to say, hey, we got these weights. I'm going to just take an average of all my hidden vectors based on these weights. Okay, so in the sense that, let's say this is alpha 11, alpha 12, alpha 13, alpha 14 is 0.7, 0.1, 0.1, 0.1. Okay, they sum up to 1. What I'm going to do is multiply 0.7 with the first hidden vector, 0.1 with the second hidden vector, 0.1 with the third hidden vector, 0.1 with the fourth hidden vector, and then sum them up together. So it's just a weighted sum of these normalized, it's just there's normalized attention weights times the hidden vectors. Okay, let's call it Z1. Okay, so this is the vector which we think is going to be very useful while producing the first decoded output. Okay. So what do we do with the Z vector that we produce? We're going to use that and the current hidden vector together to produce these output scores from which we can produce the first word. Okay. So previously, if this attention mechanism was not there, so think of this area where I'm showing the kind of trying to show a box. Let's say that was not there. Then what would we do? We just pass the input, produce all these hidden vectors, take the last hidden vector, give it to the decoding part, and then that would just create a hidden vector. And then from hidden vector, it would directly try to produce the output word. Okay. Instead of that, what we're doing is, hey, produce the hidden vector, but don't directly try to produce the output word he or he. We're going to use the hidden vector and an attended hidden vector together, maybe concatenate them, and then produce the output word he. Okay, he. Okay. In fact, we'll just concatenate. So ZT and ST, or Z1 and S1, for example, we'll concatenate them, do a linear transformation, and then take the softmax. Okay, so it's just adding that information which we think is more useful while producing the first decoding output. Similarly, when we're trying to produce a second decoding output, okay, it may turn out the right word that you want to focus on is actually the last word on the input side. Okay, so again, we're going to use the second hidden vector, use the second hidden vector with each one of them to produce attention scores, normalize them so that they are probability masses, use the probability masses to again weigh the inputs, these 4 vectors, produce a final vector. That vector concatenated with the current hidden vector together again produces the second word. So then that's exactly how we produce the third word and fourth word. Okay, so and maybe there are more words here. In fact, there are 6 words here, but this is how you produce. Okay, so you're going from a French input sentence to an English output sentence. Okay, so this is how you would finish the sentence. So hopefully you're hoping that the last word is end, and so that's where you end the output sentence construction. Any questions here for this attention mechanism? So what we're doing here, just of it is that, so instead of producing directly from the decoder, from these decoded hidden vectors directly the words, we want to concatenate the decoded vectors with another vector. Okay, that vector hopefully is a weighted combination of all the input hidden vectors. Okay, so it's just saying, hey, if it turns out that the fourth word is more important, then hopefully I can concatenate with this current hidden vector a weighted combination such that the fourth hidden vector is kind of dominant in this weighted average, and together I'm going to produce the output vector. Okay? It's just an extra information that we're using. So we basically, instead of just relying on the final information, final hidden vector to produce this whole output sentence, at every step, we are not just relying on the final input sentence, final input, final encoded hidden vector, but we are actually using all the hidden vectors together at every step of decoding. Okay, using them together in the sense that compute attention weights, take an average, and then that's getting concatenated.
Professor, regarding the inputs of the hidden nodes here, encoder.
Yeah.
So is it always is it that we are always giving one out encoding here for the characters, or how has the vector look like?
Yes, so these inputs, so here generally think of these as ideally you should have something like a word to vec. So this ideally there has to be vector representations for these input words.
Okay.
You can potentially use one-hot encoding. It's just going to be that means that you'll have to learn the embedding of the words in addition to so you will need an n dot embedding, for example. You need some vector representation for these words. Yeah.
Oh, okay, cool.
Yeah, first time you see it, it seems, hey, we are adding a lot of complicated stuff to decode. But the idea is, at the high level, the idea is kind of at least straightforward, right? So it's basically just saying that, hey, encoding is clear. Keep calling RNN cell, you get a final hidden vector. If I only pass that kind of restricts the information that was there in the input side, because all these previous hidden vectors are somehow not used while decoding. And this mechanism is just a way to say, hey, let's start decoding. And we do just decoding exactly the way we were doing for image captioning or auto reply before, except that when we're doing the decoding, we produce these hidden vectors on the decoder side, which are these green ones. While going from the decoder vector to the output word, like he hit me with a pie or whichever is the word, you kind of concatenate some, weighted average of the input hidden vectors so that some information is there, some additional information is there that was not, that may help you, decode better. That's the idea. Okay, and that's why it's called attention mechanism. So it's called encoder decoder attention. Okay, encoder decoder attention, because there's clearly an encoder side and a decoder side. Attention only because while trying to decode, let's say the word me, let's talk about while decoding the word me, I am attending. I'm paying attention to which output, so which hidden vector on the input is useful. So I'm paying attention to which hidden vector on the input side is useful. So when I'm trying to decode me, looks like the third hidden vector is useful because it has a higher probability score here. Okay. So if you have trained, okay, we're just doing the forward pass here. So if you say, hey, if I gave this word in the sentence in French, then I'm gonna decode it this way. This is just a forward pass. If you actually do a decoding, let's say at test time, you say, hey, I passed a sentence, I got another sentence. You can actually go back and see, hey, which words were relevant for which output? Okay, so which inputs were kind of important for which outputs? You can kind of do a little bit of diagnosis. Okay.
So this start vector is a flattened vector of all the inputs? No,
start is just an extra token. Just think of it again, it's just an extension of the vocabulary, so that you can say, hey, this is now we need to start decoding. So the start token is just like a special word.
Okay.
Yeah, it's just a word, regular word, just to say, hey, let's now start decoding. Yeah. So you can think of, instead of start, you can always pass all the zeros if you want.
Or some random number we can pass it. Random generated.
You could, but the architectures that you'll see today, for example, everybody, they do pass a special token. They actually explicitly capture, they create a word, they create a vector representation for these special tokens like start, end, and so on.
Okay.
They don't do random inputs there.
Okay.
Okay, so whatever we saw diagrammatically is going on here, which is that basically all the new thing is only on the decoding side. So what you do is at every step of the decoding, you get the decoded hidden state. And then what you do is for every hidden state on the input side, you compute these attention scores, right? Which are just take each of the hidden encoder hidden state and the current decoder hidden state, and then produce these scores, normalize them. Okay, so apply softmax, get the normalized version, which is alphas. Okay, alphas at this step, and then use the alphas to get the weighted average of the hidden encoder hidden states, which is the ZT. Take the ZT, concatenate with ST. Okay, that just doubles the vector length. And then, while producing the distribution, while producing the scores of your vocabulary, you just take a concatenation of the decoder hidden state and this weighted encoded state from the attention mechanism. Okay, so this is just a very it's a mechanical thing. It's not that you have to remember each of these details, but the high level ideas should be clear that while trying to decode something now, I may want to rely on not just the final thing that was passed to the decoder, right? But also maybe the hidden vectors that were created while the input was getting processed. Okay? That's the key crux of the idea here. Now, what is this function f, right? So the function f, as I said, could have parameters or could be as simple as just take an inner product between the hidden vector, the encoder hidden state, and the decoder hidden state. So as simple as like an inner product, because you just need a number. Instead of an inner product, you can also do, hey, let's add an extra weight matrix in between, like whose parameters you may have to train. Okay. Similarly, instead of just an inner product, you can do a little bit more complicated stuff. But these are just choices. Okay, these are just people have tried to figure out certain types of attention may do better than the other. But I would say there's no clear winner. I mean, there's just choices that you can try and see which attention works. If attention is really making a big difference in your application, then it's worthwhile to spend some time on what attention mechanism is better. Okay. Okay. So yeah. So I don't want to repeat this slide because we just saw the attention mechanism there. So I will skip this. Yeah, so I'll skip this slide deck. Sorry, these last few slides, because it's exactly the same as this diagram. If you understand, this animation here with this language from French to English, then you will understand attention, this encoder decoder and attention mechanism directly. You don't have to look at the last few slides. Yeah. So any questions here? And great questions so far, by the way. I mean, first time you see it, it's unclear because we're using a lot of English words like attention. What does attention mean, right? It just means exactly what we've been discussing so far. It's just relying on other, additional encoded hidden states while trying to produce a decoded word. Okay, the words are the words when you're doing a decoding process. Okay, that's all it means. Now what we'll do is actually go to today's objective. As I said, today's objective is to get a feel for what is called self-attention. Okay, so it's going to have very similar idea, relying on additional information while producing the current output, but it's going to be a core component of a new architecture. Okay, so for the rest of today's session, let's kind of not worry too much about RNNs. We really have to kind of reset our minds. We want to look at a new architecture. Okay, it's called a transformer architecture, and it will have a core component, core sub-block. It's called an attention block. Okay, so we'll look at that, and there will be some vocabulary, in particular keys, values, and queries. We saw that in the lecture goals. So keys, values, and queries, and we'll try to understand what those are. It's just a name given to some vectors. Okay, so vectors are matrices, and so we'll give kind of understand how they contribute to self-attention. And then, as I said, towards the end, once we understand transformer architecture, if we have time, we'll talk about how to use it. If not, early on next lecture, we'll talk about it. Okay, so let's get started. What I'll do is actually not do recap of attention in sequence models, because that's exactly what we discussed for the past half an hour or so. I'll directly talk about, we'll get to transformer architecture. Okay, so let me skip these slides. It's exactly the same type of animation with different, with different, I guess, illustration. So let me get to, so I want to just show at least like how attention can help in like understanding what's useful for decoding. So if you think of, let's say we have this extra attention related mechanism while doing decoding, right, in a sequence model, in the encoder decoder sequence model, then what we can do is try to understand these attention weights. Okay, let's try to look at these attention weights. Like, for example, let's say the encoder hidden state. So for example, there are 3 words on the input side. Then what we can see is whether how much does the output decoder while decoding, which word is important. Okay, for example, decoding the first word I, maybe the first word is important. Okay, while decoding am, maybe the second word is important. Maybe while decoding A, it seems as if the second word is important, and for decoding student, the last word is important. Okay, so those importance scores are exactly those attention weights. So you can arrange them, like as columns. So I'm decoding 4 things. So for each one, I must have produced like 3 attention weights, right? Because there are 3 input words, and so there will be 3 hidden vectors. So all I'm trying to say is that while decoding the first word, maybe the first word was useful on the input side. While decoding the second word, maybe second word was useful. And for, let's say, decoding the third word, maybe third and fourth, sorry, second and third word were useful. And decoding the fourth word, the third word was useful. So there's just a kind of, you can do diagnostic like this. Like for some example sentences, to get a feel for, is attention working or not? Okay. And empirically, it was seen that adding this attention mechanism to a vanilla encoder decoder architecture did help. Okay, and that's why we're looking at this. Yeah, and here is slightly the same type of visualization. Again, the attention weights. So again, a French sentence on the rows, and all we're seeing is for each word that we want to decode. Let's say the first English word that you can see on the as a column header. We're just looking at collection of what are the attention weights. Okay, so there's going to be 1 attention weight per input word, as I said, because there's only 1 attention weight per input or the encoded hidden state. So you can just look at, hey, what do the attention weights look like? So you can see that while trying to decode trying to get the first word D, the attention weight says, hey, maybe the first input is useful. Now, while trying to decode the English word arrangement, it looks like the second word of the input is useful. But you can see that while trying to decode, let's say, European, it can actually pick up, hey, while trying to decode European, I need to pick up not the, let's say, the 5th word, but not the 6th word, but actually the 7th word. So you can see that what is actually useful for decoding each word. You can see that. So it doesn't have to be this. Doesn't have to be like a diagonal pattern where every word on the input, every word while trying to decode on the output, there has to be exactly at that location word on the input side, right? It's not expected, and this is an example of that. Any questions here? This is just a visualization for 1 sentence pair. How is attention influencing the generation of the word? So when trying to generate European, it is actually looking at the European word on the input side. Okay, looking at it in the sense that the attention weight for that is the highest. Okay, but you don't have to do this diagnosis. You can always pass a sentence and you can get the decoded sentence out. That's just a test time, right? So at inference, you just get a decoded sentence out. If you want to understand what was used to decode, let's say, the 3rd word or the 4th word or 5th word, you can visualize the attention weights. Otherwise, attention weights will be used internally to get good decoded output. Okay. Okay, so let's actually step forward. Actually, I think it's a good time to take a break for 10 minutes because it's a new topic and I don't want to take a break, just start introducing a new topic. So what we're going to do next is look at the transformer architecture and self-attention. Okay, so let's take a break for about 10 minutes. So let's resume at 4:55. Okay. Okay, so next what we're going to do, as I said before, is really understand the notion of self-attention, which is the core of this transformer architecture. Okay, so let's actually get started. Make this full screen. Yeah, so this transformer architecture is from 2017, so barely, actually less than 5 years old. And it can also be used for sequence modeling, and that's why we are studying it right after we looked at RNNs or LSTMs. Okay, so attention. So the attention, which we saw earlier, the encoder-decoder attention, there's a similar idea that's going to be used here, and it's a core component of this model. So for illustration purposes, we're going to stick with the same application that we were seeing earlier, which means that we look at what is called neural machine translation. Machine translation just means going from one language to another. It's just translation. So we're going to again go from let's say French, some input sentence to some output sentence. Okay, so in between, what we're interested in studying now is just a forward pass. Again, how does inputs go through and create our output sentence? Okay, so just like how we did for RNNs. Okay, so we're going to open up this blue box in between. So the initial paper came in 2017, and then there has been a lot of work and a lot of variations on transformer architectures. BERT, B-E-R-T being one of them. But before that, let's actually understand the core transformer architecture. Okay, so transformer architecture somehow, either in a positive or negative way, also has some overlap with the vocabulary that we used earlier. Okay, but I strongly suggest don't relate this vocabulary here to the vocabulary there, unless I explicitly point it out. Okay, so if you think of the blue box, it still has two, I guess, sub blocks. One is a collection of encoders, and another is a collection of decoders. Okay, so these encoders and decoders, don't try to relate it to the RNN or / LSTM based encoder-decoder architecture that we saw earlier. Okay, they're not related at this point. Okay, so there's an input sentence. It goes to this collection of encoders, and that's the green box here. At the end of the day, this green box is going to produce a bunch of vectors. Those vectors get passed on to decoders, collection of decoders, and they all work together to produce this output sentence. Okay, so that's at the block level, and what we're going to do is slowly peel into one of these blocks. In fact, we'll peel into one of these encoders. Okay, so really, I said there's a collection of encoders and a collection of decoders. So really, if you think of the encoder collection, it's actually wired this way. Okay, so you can think of each. So there's a bunch of encoders connected to each other in this linear way. Okay, so there is a green box followed by a green box followed by a green box and so on. Maybe there's like you can see in this diagram, there's 6 of them. Okay. The number 6 has nothing to do with the input sentence. Okay, so there's some 6. Think of them as 6 layers. Okay, the number of layers don't change if your input has 3-word sentence or a 50-word sentence, right? So that's the way you need to think about it. So there's a fixed number of encoders. Okay, some blocks. We will open them in a second, and then you pass so you pass initial, let's say, word embeddings of the input sentence, and eventually you'll get some final outputs, which are also some sort of vectors. Those vectors are passed to each one of the decoders, as it shows here, each one of the decoders, and each decoder is connected to the other, and eventually think of them again as layers, and then eventually the last decoder is what produces the full sentence. So each encoder is taking the full sentence or something related to the full sentence. Okay, some vectors related to the full sentence. Okay, so Is the idea clear at this point? Because I don't want us to get confused at this point.
Professor.
Yeah.
Does it make a difference if we use a non-Latin letters or words?
Non-Latin letters or words, in the sense that no, it doesn't. So in fact, in your assignment, you will pick any pair of languages to use the same architecture. So you just need to, what we need typically for English, we've been spending a lot of time, but for English, we have the word embeddings. Similarly, for other languages, we do have word embeddings. Okay, it's just I'm not showing the links here, but you can get the word embeddings for many popular languages around the world. Okay, so you can always build something similar for any language pair. Okay, so there's nothing specific with French and English or any other Latin-based, languages here. Any other questions? Okay, as I said, again, I want to just repeat one thing, which is that the number of encoders is fixed. Okay, let's say 6, and we're going to kind of keep 6 till the end. Number of decoders is also fixed, maybe 6 here. It doesn't depend on the input sentences length. Okay, so whereas if you think of the encoder step in RNNs, encoder step or encoder part, it just depends on how long the sentence is. If the sentence had 10 words, then 10 times RNN cell will be called, right? But that's, let's not talk about RNNs here. So there are 6 encoders in this illustration and 6 decoders. What we'll do next is really open up the encoder. Okay, so we'll really focus on one encoder, because within an encoder layer or unit is where the self-attention mechanism comes in. Okay, so as it says in the slide, the number of such units, as encoder units, is fixed and doesn't depend on the input length. Okay. There's going to be parallel treatment of all input elements or words at the same time, each of the encoder blocks. So in the sense that if you think of the first encoder block, all the words are passed in at the same time, and some outputs come out at the same time. So let's kind of understand that. But a couple of more points before we get into how inputs are processed. Firstly, these encoder units don't share weights. Okay, so in the sense that we saw the 6 encoder boxes, they don't share weights. They all have different weights. Okay, so they have different weights in the sense that they all have to be tuned separately. Okay, not separately, but they all have separate weights, basically. Okay, unlike RNN cell, for example. Now, each encoder block has 2 subblocks. One is called a self-attention layer, and then there's a feed-forward layer. Okay, all the words, if it's the first encoder, for example, all the words will be input at the same time. I think I just mentioned it in the last slide. The feed-forward layer is going to be such that there's going to be some reuse of weights inside the feed-forward layer. Okay, remember, if all the words are being passed in the same time, there could be 10 words, there could be 3 words, there could be 20 words. It doesn't matter. So however many number of words are there, this feed-forward layer kind of does some weights, reuses the weights to process each word. Okay. We'll get to, when we open the feed-forward layer, it will become more clearer. Now, on the decoder side, it's exactly the same sub-blocks. Okay? There's the self-attention block, and there's the feed-forward block. But in addition to that, there's going to be an additional block called the encoder-decoder attention. And this is exactly the attention that we saw right before the break. Okay, so there's an extra layer, kind of isolated, self-contained. And remember, even the decoder's objective is to produce those, output translated words or whatever they are, right? So translated sentence, okay, and it could be variable length. But we'll see how this decoder works later. Let's first understand how the encoder works. Okay. So really now we have zoomed into the encoder, and for ease of kind of understanding, let's really look at the first encoder. Okay. The first encoder is just connected to the inputs or the word vectors corresponding to the input sequence. Okay, so for example, this French sentence, let's call x1, x2, x3 the input word embeddings for these 3 words. Okay, so although there are three word embeddings being shown here, the encoder architecture, or in general this transformer architecture, the encoders, they kind of, you need to pre-decide how many words you're going to process at max. Okay? Which means that if you, for example, in this slide, you can see that there are 3 words being passed. Okay? What if the sentence had 20 words? What if the sentence had 15 words? What if the sentence had 5 words? So although the sentence length varies, the encoder, you kind of pre-decide in the sense that at the architecture level, you say, hey, the maximum number of words I can process is some fixed number, like 20. Okay, so, which means that you cannot process a sentence which is length 21, for example. Okay, but you can certainly process things which are less than length 20, because you can always input zeros, right? If a sentence doesn't have, for example, if the encoder can process at most 20 words, if my sentence only has 3 words, then the remaining 17 words that I was supposed to pass in, I'll just pass zero vectors, for example. Okay. And let's assume that the embedding size is something like, let's say 512. That doesn't matter for now. So although I'm talking about the first encoder layer, this outermost green box, the the other encoder layers that follow it will have very similar, in fact, it will be the same, except the input are not going to be word embeddings. The input are going to be just the outputs of the previous encoded encoder unit. Okay, that's all. So now let's look at the inside of the encoder block, right? So as I said before, there's the feed forward, there's a self-attention layer followed by a feed forward layer. Okay, the self-attention layer takes all the words, all the inputs at the same time and produces one vector corresponding to each of the inputs. Okay, so if the input is x1, x2, x3, it's going to produce output z1, z2, z3. Okay, now z1, z2, z3 together, all the 3 C vectors together are fed into the next feed forward sublayer, and then they produce some final output vectors. Okay, so those are the vectors that get passed on to the next encoder unit. So the important idea, and we're going to kind of zoom in on the self-attention part, is that I'm going from x1 to z1, right? So for each word basically on the input side, there's always going to be some vector at any encoder level. Okay, so either the self-attention output level or the feed forward output level or any encoder output level. Now the vector output at the self-attention layer, it has the interesting property that this vector really depends not just on the input vector of the word that coordinate is related to, but it also depends on the other words. Okay, so for example, the z1 depends on both x1 and x2. Okay, so here I changed the input sentence from the French sentence to an English, I guess, input for simplicity. But basically what I'm trying to say is that the idea for self-attention is that z1 really depends on x1 and x2. Whereas R1, which is the output of the feed forward network, just depends on Z1. It's just some sort of linear transformation of the input. I mean, I'll talk about it later, but Z1 to R1 is just some sort of the typical layers that you've seen in RNNs or feed forward networks and so on. What's interesting is that Z1 itself is an output which depends on both x1 and x2. Z2 is an output which depends on x1 and x2, and so on. Okay. So before opening up the self-attention, how does Z1 depend on x1, x2? Let's talk about why does it, what is the implication, right? So implication is that, let's think of this illustration here, where there is a vector for each word. So D has a vector. Let's call it, there's a vector, row vector here. There's a row vector for animal and so on. I'm not showing the vector here. What I'm trying to show is the some sort of weight, importance of these vectors. Okay, if you think of, as I said, after the self-attention, there's going to be an output. There's going to be an output vector. Let's focus on the output vector for it. Okay, that output vector in this illustration is trying to show that the output vector is heavily influenced by the inputs D and animal. So kind of it. Informally, it refers to the animal. And so the output vector for it is heavily influenced by the vectors which are related to D and animal. Okay, that's very similar to the attention idea that you saw with the encoder-decoder attention. Okay, so it's basically trying to provide vectors for words or outputs for words which really attend to the appropriate words while getting their representations. Okay. So you get a better encoding for the word it. That's what's going on. So let's actually now talk about how does Z1, for example, depend on both X1 and X2, okay? Or how does Z2 depend on both X1 and X2? Okay. We'll really tease it down at the level of like just matrix vectors. So let's say we have, we're the first encoder unit, and we have X1 and X2 passed as inputs. Okay, so the original input was thinking machines, the English words. From there, we got the embeddings, and let's say there are pre-trained word embeddings, word to vec if you want, X1 and X2. What we do in the self-attention layer is create three vectors. Okay, create three vectors, Q1, K1, and V1, corresponding to the embedding X1, and Q2, K2, V2, corresponding to the embedding vector X2. Okay, so basically, each embedding vector is resulting in three new vectors. Okay, so Q1, K1, and V1. Okay, now Qs are called queries. The ones with symbols K1, K2 represent keys, and ones with symbols V1, V2 represent values. Okay, so it's just some vectors being generated from the original input vector. Okay, how are they getting generated? Just think of a weight matrix, multiplying the input vector to produce the output vector. Okay, so X1 times something like WQ produces the Q1, X1 times WK produces K1, and X1 times WV produces V1. Okay, similarly, X2 times WQ produces Q2, and so on. So now what we did is we got the two initial input vectors from which we produced three smaller, potentially typically smaller dimensional intermediate vectors called queries, keys, and values. Okay? So there are specific names that are given to this, and that's because of this type of operation that we're going to describe next. Okay, once you have these three vectors, what do? So once you got these three vectors using those three matrices, and remember those matrices again, think of them as weights. They need to be learned. These are the parameters of the self-attention layer. Okay, they need to be learned. What you do with queries and key vectors is that you just do an inner product between them. So queries times keys, you get some final scalar value. So what do you do? Now let's talk about how do we get Z1 from both X1 and X2. Okay, so what do? We look at the query and key for we pick the query for the first word. You multiply query Q1 with key 1 to get some score. Now use the same query to multiply it with key 2 to get some score. Okay, so the query is really to multiply it with every key vector. Okay, so if there are only two words, you multiply it with two keys. If there are 10 words, you multiply the same query with 10 keys. Okay, because remember we are trying to generate the Z for this word. Okay, Z1 for this word. Okay, you got two scores. Now you can imagine what do you do with scores? You can kind of scale them down. Maybe divide by in this case divide by 8 for some reason. Some scaling constant. Okay, divide by x. Divide by some constant, and then you have two numbers. Again, you apply softmax. Okay, it's very similar to the attention mechanism we saw at the beginning of the lecture. So it's just you have two numbers which are not between 0 and 1. You want to make it between 0 and 1. So you do a softmax operation. If there are 10 words, you just do exactly the softmax operation. There'll be 10 numbers, and then there'll be 10 numbers in the last row, which sum up to 1. Okay. Now, what did we do so far? To generate the first word's final Z1, which we're getting to, we use the query for the first word, and we use keys of all the words. Okay. The only thing remaining is somehow we want to use the values of all the words. Okay. So, and that's what we're going to do. So we got the weights, these kind of attention weights, okay, from using the query and the keys of all the words. Okay, we got the attention weights. Now we're going to just multiply them with the values. Okay, just multiply 0.88 times value 1, 0.12 times value 2, and then just sum them up. Okay, so just multiply by the weights, sum up the values, and that's the output. That's the Z1 vector corresponding to the first vector, corresponding to the first word. So we started with the embeddings. We got the intermediate queries, keys, and values. Use the queries and keys to produce, these types of attention weights. Bunch of weights for each word, and then use the weights and values together to produce the weighted combination, which is the Z1. Z1 for the first word, Z2 for the second word. Same type of operation. Any questions here?
Professor?
Yeah.
This Q1 and K1 is element-wise multiplication or a matrix multiplication?
It's a inner product. Okay, so I didn't write it properly here. It's just an inner product, element-wise multiplication, and sum it up.
Okay, thank you.
Yeah. So if you really, so the next couple of slides are just showing the vectorized or whatever vectorized version of this, where we are just instead of looking at separately, hey, there's all these separately, we just put the embeddings one below the other as rows. And then we're saying, hey, if given this embedding times this query matrix, will give you the query vectors. Again, one row corresponds to each word. So if you had 10 words, then 10 such rows for the query matrix. Similarly, embeddings multiplied with the key matrix will give you the key matrix, and similarly the values matrix. Okay? So you actually do matrix multiplication. That's why GPU helps. Okay. Once you get these matrices, you can actually just do a matrix multiplication, which is exactly what I showed in the 2 slides ago. It's just the matrix version of the whole operation. So you get the keys. So you get the query matrix, you multiply it with the transpose of the key matrix, and you get a bunch of you get a resultant matrix. You multiply it with a constant, and then take a softmax operation, and then you multiply it with the value matrix. Okay? So it may be hard to understand what's going on in this slide directly, but this is exactly the operation going on. You just have queries, keys, and values for each word, and you just take a query for each word, multiply with keys of every other word, including itself, get some attention weights. Weighted average of the values will just become the final output. Okay, that's what's going on. That's the output here. It's just shown in a vector, very quick shorthand notation. Okay. And so this step, for example, should look very similar to how we did it in encode decode intention. So there's some weights and there's some values that were pre-generated. We're just doing a weighted average of these values to be the first output, weighted average of these values to be the second output, and so on. Okay, so that's what we're doing. Okay, so next is a second important concept. The first concept was understanding self-attention. Okay, so so far what we've done is this is a self-attention. Given the input embeddings or inputs, you get these intermediate matrices and do this operation. You get final vectors. Okay, output vectors. Okay, this is the self-attention. Self-attention because while producing the output for the BERT thinking, you are looking at what other words came with me, right? So in addition to thinking, there was machines, and so that will also influence what the output should be. So that's why it's called self-attention. Okay, it's not it's different from the encoder decoder attention that we saw at the beginning of this lecture. So the self-attention just means while producing the current output, I rely on the outputs or the values of all the other words that are simultaneously appearing with me in the input sentence. So that's why it's called self-attention.
Professor, how are these Z1, Z2 or corresponding vectors? Is there any relation between them?
Between Z1 and Z2? No,
Yeah.
so Z1 is produced using a weighted combination of V1 and V2.
Okay.
Similarly, Z2 is also produced based on a weighted combination of V1 and V2. But that weights are going to be different, right? So remember, these weights 0.88 and 0.12 were obtained by multiplying Q1 with K1, Q1 with K2. A different set of weights will be produced when you use Q2 times K1 and Q2 times K2. And then just Z1 and Z2 are just like a weighted average of these value vectors. Okay, these value vectors. That's what this is. Here, we're just showing if you multiply 0.88 times this, it just remains as this. 0.12 times the original value vector, it kind of gets faded away. And then you sum them up. That's your Z1 here. And similarly, Z2 will be some weighted combination of V1 and V2.
Okay, so I was concerned about the similarity between Z1 and all the corresponding vectors. Will similar words be similar, having similar Z1 score vectors?
So the point is that Z1 should be influenced by what other words are there in the sentence. So for example, if you go back to this example, the vector for it is getting influenced by what was the vector for the animal, because it actually should correspond to the animal, right? The animal didn't cross the street because it. What is it? It's actually the animal. So you're trying to kind of say that, because you're doing, let's say, the linear combination of these value vectors for each of these words, the vector for it should kind of be very close to what is the vector for animal. Of course, the vector for animal may be itself, for example. That's what we want to show through this illustration. So yeah, these all will be related in the sense that they're all weighted combinations of the value vectors. But hopefully they are for example, you can think of a situation where D vector at the output only depends on the D vector at the input, and animal only depends on animal. Didn't only depends on didn't. Okay, that can happen as well, right? So think of these weights, right? Like these weights here. For example, instead of 0.88 and 0.12, what if it was 1 and 0? That means that whatever vector we produce for thinking is the only vector that influences Z.
Okay,
right?
so yeah, so I get that, but since we are using word embeddings, let's say for different words, our inputs are embeddings. So
Yes.
so aren't these embedding itself similar if they are similar? So doesn't it dampen our effect of
no,
our
word
output?
similarity is fine, right? So that is just a better representation of the words. At the end of the day, we want to work with natural language. We have to have numeric representation for them. Whether the numeric representations are, themselves capturing semantic meaning or not is not kind of important here.
Okay.
In the sense that they are not, they're not counteracting anything here. Okay, so we ideally want some vector representation of the words, and then for our task, which is to decode, right? Remember, we are trying to do translation. For our task, we want to say, hey, so the whole point is very similar to what we saw here, right? While trying to decode, let's say maybe we want to translate the word it. We have to know what does it correspond to, right? So that's all is going on here. So whether the embedding for animal is close to the embedding for bird versus embedding for house, that is not kind of, it's not a big issue here. It's not something which is counteracting this mechanism.
So does it help if not counteracting? So does it help in?
Yeah, it could help. It could help. Yeah. Word embeddings by themselves do help, right? So similar words, semantic meaning of words helps in further processing. Like for example, instead of the animal didn't cross the street because it was too tired, instead of that, the animal didn't cross the road because it was too tired. Road and street hopefully have similar word embeddings, and hopefully that will help in the translation, for example, whatever is the task going on. Yeah.
Okay, sure.
Okay, so the first idea was self-attention, that words somehow kind of rely on other words and can figure out, hey, these other words are related to me while I need to be decoded, for example, in a translation setting. But it could be not just translation; it could be auto reply, it could be speech to text, or text to speech, or it could be question answering. It could be many other things. Okay, these are all very rich applications which are not like typically seen in supervised learning, like a first class in supervised learning, first ML course. So the next concept with transformer is the idea of multi-headed attention. Okay, so we saw the attention mechanism that we went from embeddings or whatever inputs to the encoder, inputs to the self-attention sublayer, to some outputs of the self-attention layer, right? Some Z1, Z2. The idea of multi-headed attention is that you start with the original X1, X2, but instead of just producing just one pair Z1, Z2, you actually produce multiple such pairs. Okay, which means that you start with let's say this X at the top. You produce queries, keys, and values, and eventually you get Z1, Z2. But again, you start with the same X. Again produce queries, keys, and values, and produce another set of another Z1, Z2. Okay. Now, why am I saying another? Is because these weight matrices, which produce the queries, keys, and values, they will be different. Okay, they will be initialized different, and then if you do gradient descent, they may not be eventually they may not all be the same. Okay, they may do their own different updates, and they'll all be different typically. Okay, so why are we doing this duplication? Right, the duplication has some empirical support. The duplication seems to help in this whole attention idea that when the word like the word thinking may depend on machines or may not depend on machines, that is captured via this attention mechanism. But if you can imagine for longer sentences, sometimes you can get different representations when you do multiple attentions. So let me actually show you in the next slide. Actually, 2 slides from now, how does that plays out? Actually, let me show it here, and then we can go back to multi-headed attention computation. So it's the same sentence. The animal didn't cross the street because it was too tired. And you can see what you're seeing on the orange column corresponds to attention weights for one attention head. Attention head, just think of this as like one attention operation, self-attention operation. The green column corresponds to another attention operation, like different keys, queries, and values, and then the attention weights are being shown here. Okay, so again, the word it, you can see that the orange one is actually focusing on the animal, and then in the on the green, this is the second time I'm computing the attention attention outputs, self-attention layers outputs. Then it's focusing on tired. Okay, so you can kind of, this is just one example, just for the illustration's sake, we're just seeing this, that maybe it, the word's representation, not representation, but the word's, the word's output, the output corresponding to this location, this word may be influenced by not just is influenced by the animal in one attention computation, and is influenced by tired in another attention computation. So it's complementary information. Okay, so that's what is being said here, is that if you do attention computations multiple times, potentially eventually the Z1s that you get, for example, for thinking, they may be influenced by different parts of the input. Okay, which is just more flexibility compared to a single attention head. Okay. And so how do you do that? So it's exactly shown here. So if you start with the same inputs, but now you produce multiple Z1, Z2 pairs, for example, if there are 2 words. If there are 10 words, there'll be multiple Z1 to Z10 pairs. Like here, you can see 8 attention heads. Okay, so 8 attention outputs. Okay. Now, but the problem is I don't want 8 attention outputs. I still need to pass something to the next feed-forward layer. If you remember the encoder unit, then what you can do is actually combine them. So if you have 8 outputs, you can just concatenate all of them and somehow reduce it back to, let's say, 4 dimensions that you wanted to go to the next sublayer. If you remember, there was a feed-forward sublayer. So you can just merge them together by, again, linear transformation. So there is some parallel computation 8 times, and that's why it's called multi-headed attention. So you're doing multiple values of queries, keys, and values, and then producing the Z's, and then you're merging them back together using a linear transformation. And that's what is passed on to the feed-forward layer. Okay.
Professor, this multi-head attention will solve our problem that one word with different meaning, like an apple. Apple is a company also, apple is a fruit also.
Yeah, it could. In the sense that, see, attention is not about disambiguation. I mean, it could be related. What you said is about word sense disambiguation. So whether an apple word appears in some context, whether it's referring to fruit or a company, that's certainly a problem in the language. But here it's just about which words to attend to get a better representation for the current word. Okay. So it's just whether it in general by itself, if you think of word embedding for it, if you just took off the corpus of all places where it appeared, it's unclear which, what is it referring to. It'll have its own embedding, but in the context of the sentence, maybe it should refer to the animal, and maybe it should be influenced by what is happening to the animal, maybe. Okay, so that is just that contextual information is being captured in this word representation, but disambiguation by itself is probably unclear. It's unrelated. Maybe it does deal with disambiguation as well, but that's not the direct. That's not the reasoning here.
Okay.
Yeah. Okay. So I will not. So as I said, like once you get the z vectors, you can multiply, concatenate them and multiply with the matrix so that you can eventually get only one z vector. Okay. So it's just a typical feed-forward network. And this slide is just showing the same, the whole operation starting from some embeddings. Either if it's the first encoder, it's the first encoder unit, that will be the original initial word embeddings. If it's the second, third, fourth, fifth, or sixth encoder, then whatever is the input, whatever is the output of the previous encoder is the input. Okay, and you'll produce 8 such queries, keys, and values, 8 such outputs, and then you multiply and eventually concatenate and multiply, so that eventually you get only one collection of like outputs for the self-attention layer. Okay. But although I gave you this illustration that, hey, maybe this illustration is showing that it may be related to animals and tired, it doesn't always work that way. So here, here actually you can see there are 8 attention heads, Okay, so you can see each. So at the top where I'm showing my pointer, there are 8 different colors. So you can see if you look at all the attention weights of all the different attention heads, some of them don't make sense. The orange and the green is where we were focusing on the previous slide. So orange here, green here, but the other ones, there's not much sense. Like why are you attending here? Why are you attending, here or here? It's unclear. Okay, so it's visual. Whenever people give you visual examples, it's just for illustration's sake. Not all examples work like that. It's just for like understanding, how it might help. Okay, just a disclaimer there. But empirically, it really does improve over single-headed attention. Okay? So, and that's why it was, that's why it was kind of, that's why it's part of the standard architectures and standard transformer architectures. So actually that kind of covers the core component, which is self-attention, and multi-headed attention is just repeating the same thing a few times and then concatenating. There are a few more things. So that's, we focus on the self-attention sublayer. We'll come back to the full picture of the encoder in a second. There's one more thing that now what we're going to do in the next few slides is just talk about a few more bells and whistles, because the core component of transformer architecture is just a self-attention block, because the remaining stuff is just feed-forward layers and then some way they're wired. We'll comment on them, but everything else is kind of transparent if you understand what the self-attention sublayer is doing, okay, which was a part of each encoder, right? So what we're going to do next few slides is just talk about a few other considerations that have been used, okay? And first one is positional encoding, okay? So if you imagine in RNNs, for example, if I have a sequence of words, then I do capture sequence because I pass the first word first, then the second word, then the third word, then the fourth word. So there is some order relationship, and it is being used while doing RNN processing, right? Whereas here, you can see that if I'm doing self-attention, there is no, there is no order relationship that is captured. Okay, so for example, right here, whether thinking precedes machines or machines precede thinking is irrelevant, because I just need to get queries, keys, and values, and do some softmax, get some weights, and then take a weighted average of the values. So whether if I swap the location of thinking versus machines, it doesn't change the Z1 and Z2. Okay, so somehow it's a issue here, which is that order doesn't matter, at least in this processing. So we need to somehow inform about the ordering of the words somewhere else. Okay, somehow take that into account somewhere else. Okay, and that's captured here. So that's captured only at the input. Okay, so the input right before we pass word embeddings to, for example, the first encoder unit, we do one extra, I guess, intermediate step. Okay, which is called positional encoding. It's just basically trying to ensure that hey, this is the first word, this is the second word, this is the third word. That's what we want to kind of inform, or at least capture, explicitly add that signal before passing the words into this encoder collection of encoders. Okay, so how do we do that? It's actually seems counterintuitive, but what we're going to do is actually we have the original embeddings that you can see at the bottom. So we have the original input, the words. Let's say we got the embeddings x1, x2, x3. What we're going to do is add vectors. Okay? Add vectors t1, t2, t3. Then we'll have a resultant vector x1, x2, x3. And then those are the vectors that will pass to the encoder units. Okay, so this x1, x2, x3 somehow will be modified versions of the original word embeddings, with the modification being there's some addition of some vectors, and those vectors ensure that there is an order signal in those vectors. Okay. So let's think about it naively, right? So how would we impose order? So for example, what you can do is, hey, give me the original embeddings. Let me add one extra coordinate saying, hey, this is the first word. One extra coordinate saying this is the second word. One extra coordinate is saying that this is the third word, and so on. You can do something like that, right? So you just say that, hey, this is the first word, this is the second word, this is the third word. It's the same, I guess, spirit, right? The way we are going to add some extra vectors such that there is a distinct signal that's part of x1, such that we know that x1 precedes x2, x2 precedes x3, and so on. Or the word, first word precedes the second word, precedes the third word. Okay, that's the intention behind this positional encoding, I guess, pre-processing step before the sentence is passed into the encoders. Okay, so what is this positional encoding? As I said, this is an addition. Instead of adding an extra coordinate saying this is position 1, 2, and 3, this is word 1, 2, and 3. What they typically do is add some sort of a predetermined vectors, predetermined collection of vectors, which have some ordering. Okay, some values in those vectors, but they are such that they have some pattern. Okay, some sort of deterministic pattern, which kind of gets picked up by the network to kind of, if the network needs to know that, hey, the first word precedes the second word, the network will pick up from these patterns. Okay, although they are added into the word embedding, still the network figures out that word 1 is before word 2 and so on. Okay, so we're not changing anything about the network. The network is exactly what we said before: bunch of encoders, bunch of decoders. Each encoder has self-attention sublayer and a feed-forward layer and all that. So it's all the same. The only thing that's changing is inputs are not passed as is. They're just getting added with some extra vectors. Okay. So if the input embedding is 4-dimensional, then the extra vector is also 4-dimensional. It looks like this. In reality, how do they look like? Right? So here's an example from one type of vector. So each row, by the way, each row corresponds to a vector. Each row, although you may see a sharp discontinuity here, don't worry about that. Go from, all the way from left to right is one vector. So how many rows there are? There are 20 rows, okay? 0 to 19, whatever, 20 rows. And how many columns are there? There are 512 columns. Okay, so think of this, it's like pre-generated vectors. Okay? It's like somebody generated and stored it in database. Every time you want to pass an input, you kind of pick each one of them. So if you have a 3-length word sequence or a three-line sentence, then you pick the first 3 vectors and add them to the word embeddings, and then you pass it to the transformer. Okay. Here is another one. This is like 10. There's like 10 positions or 10 words, 10 word locations, and then it's like a 64-dimensional embeddings. Okay. So just giving a sense of like how do the patterns look like. It's not really informative. All I'm trying to say is that this addition of this noise somehow helps the network learn that, if it needs to learn that word 1 is before word 2 or is before word 3. Okay. I mean, if that information is useful for doing some decoding, that it'll pick it up. Any questions so far?
Professor, if we add some positional encoding vector to the original vectors x1, isn't there a possibility that the word embedding that corresponds to x1 is changed in such a way that it actually corresponds to some other word embedding?
Yes, there is a possibility. Yes, definitely. But the possibility is quite rare, but it is still there. It is still possible. Yes, I agree with you. But as you saw the definition of the self-attention subblocker, it just doesn't have, it's invariant to ordering. And so, but we want a sequence model. So there has to be some sequence information somewhere. So we're adding it here. Okay. Otherwise there is no sequence information being captured at all. But a good point, nonetheless. So, I mean, there could be, as I said, the idea is really like you can think of adding extra coordinates saying, hey, this is word location 1, here's word location 2. You can literally put in the numbers, right? So 1, 2, 3, if you want, as an extra coordinate. And that's also saying that, hey, this is the first word. This is this explicit feature vector saying, hey, this is the first word, this is the second word. If you want to do that, you can do that as well. So people have figured out by experiments and so on that this is one good strategy to do. Okay, let's actually look at now let's actually kind of complete the understanding of our encoder unit. As I said, there is a self-attention layer, and that's what we spent quite a bit of time in the previous few minutes. The self-attention layer, which is shown in the orange. What I'm also trying to show in this figure is kind of pretty much the full picture of what all goes inside the encoder unit. So the self-attention is where we spent much of the time. The extra information I want to show in this slide is that there's this dashed lines that you can see. So there's vectors going into the self-attention and some vectors going out. So thinking of, x1, so this plus sign just means that there's some positional encoding going on. So you can see that positional encoding is this extra plus sign at the bottom. Then those vectors are going into self-attention, the first encoder unit. And then Z1 and Z2 got out, right? Z1 and Z2 after like multi-headed self-attention, in fact. Then what's happening is there's a green block, which is called add and normalize. Okay. It's not really a layer. It's like what you would call like a polling layer. It's like that. It's not really, there's no parameters there, but there is some extra operation going on. It's just, and I'm going to comment on it in a second. But the important thing is there's also this skip connection. Okay, so there's this connection dash line that the same vector that got into self-attention, into the self-attention, is also being used outside of self-attention. It's like skipping the self-attention step. Okay, so the skip connections are also, by the way, important aspect of residual networks. So in assignment 2, in question 1, you've been using ResNet 18, right? So if you actually, if you're able to look at its wiring of, hey, what are the layers in the ResNet 18 neural network? It's not exactly the CNN architecture that we saw. Okay, it has some extra things, which are what are called skip connections, residual connections. Okay, and in fact, that's what gives it the name ResNet. Okay, ResNet is uses the first prefix of the word residual. Okay, so these are called residual connections. All they're doing is, hey, you did some processing, but let's also retain, just add back in the original vector as well, in case some information there is useful for later layers. Okay, so that's what's going on here. So there's residual connection with after the self-attention, also residual connection before and after the from before to after the feed-forward layer as well. Okay, and feed-forward layer is shown separately here because this feed-forward layer, just think of it as is just a matrix transformation. So it's just like one layer of a neural network. So whatever vector is here, you just add multiply with a weight matrix, add a bias, and just pass it forward. Okay. Now, I have not yet discussed is what is add and normalize. Okay, that's the only thing missing. Is the residual connection clear? It's just so just think of these as like adding up so clearly, there are two vectors being inputted here. They just get added, and then that's passed on forward after doing some extra normalization. And I'm going to talk about normalization in a second. Okay. I don't want to confuse, and it's not important to memorize all this. It's just that this is what people architected back in 2017 and 18 and so on. And people still, especially deep learning researchers, this is what they're kind of work on. One part of their work is about building the right, building blocks, which capture more information, which help to improve performance in translation or whatever is the task that they're working on, right? So this is about residual connections. Now let's talk about what is happening in that green box, right? So in the green box, as I said, you have this x1, x2. So let's focus on x1 column here. So x1 got z1, that we know, multi-edited attention, and then x1 is also being passed as input to this green box. Okay, so z1 is getting added with x1. So let's say so you can see here x is getting added with z. Okay, so that's what's going on. It's just showing in vector version, but you can just say, hey, z1 and x1 are getting added as well. Okay, so the row-wise addition, right? And then there's an extra operation called layer norm. Okay, so that's the that's what it's called normalization. Now, layer norm is a very similar idea to batch norm. In fact, it's simpler. Okay, so remember batch norm from lecture 3, right? So there was some normalization that we were doing between layers. So here, layer norm is a simpler idea than batch norm. All it's saying is, hey, you did this addition. Eventually, you got some vector, right? For each word, you got some vector. What I'm going to do is just take, subtract its mean and divide by the variance of that vector. Okay, so just subtract its mean and divide by the variance at each vector. So first word, there'll be some bunch of numbers. Just take the mean, subtract the mean, and divide by its variance. Okay. Similarly, for the second word, there'll be a bunch of finally some vector will be there. Subtract the mean and divide by the variance, and then that's what you pass out as this z1 and z2. Okay, and that z1 and z2 get through feed-forward network, and exactly the same layer-wise, same addition and normalization happens here, and then that's the final vector that's being passed out. Okay. So in fact, layer norm here's a snapshot from archive, which says what is going on with layer norm. Okay, so it's just literally computing the variance, mean and variance, and use that to normalize. So it's very similar to finding z-scores. Okay, and there's nothing to do with batch here. It's literally at the level of each word or each word's vector, you're just doing subtracting the mean and dividing with the variance. Okay, estimate, empirical variance. Oh, sorry, dividing by the standard deviation. Sorry, not variance, but yeah. So it's just computing something like z-scores given each vector. So this is actually the full-fledged encoder unit, and now you can imagine there are 6 of them, one connected after the other. So it's quite a complex network to be really, if you really want to look at it fully, right? But what we did, just to recap, is really look at what's happening in self-attention, looked at the single version and then the multi-headed version, and then discuss this residual connection, discuss the positional encoding, and also finally discuss the layer transformation. Okay, sorry, layer normalization. Okay, and this part we did not discuss, but it's just feed-forward. It's just a weight times input input vector times plus bias. Okay. So, any questions about different moving parts of an encoder unit? Okay, so what we'll do is now talk about the decoder unit. Okay, so we kind of almost, this is by the way, this is the most complex lecture in the whole course. So we'll try to wrap up this. So we have actually kind of gone through most of the details of the encoder. The only thing remaining is we saw that the decoder has almost the same parts except for one extra thing, which is the encoder-decoder attention. Okay, and we'll see how decoder works, because decoder again will have to work very similar to how it was working in the RNN case. So it has to generate one word and then another word and then another word and so on. Okay, so in this diagram, in this slide, we're just showing 2 encoders and 1 decoder. Okay, but actually 2 recorders, but 1 decoder expanded. Okay. It's just to show you the full connection picture. So what's going on is that on the encoder side, we started with the embeddings. Okay, we added positional encoding and passed through a bunch of encoder layers. In this case, 2 encoder layers. What we get at the end is a collection of vectors, right? So collection something like Z1 and Z2, right? What we do with the Z1 and Z2 is actually we don't just get Z1 and Z2, but we also create queries, keys, and values. Okay, so from those final Z1 and Z2. So in fact, the encoder's output, all the encoder units eventually produce queries, keys, and values, where there's going to be 1 query per word. Okay, 1 query per word, 1 key per word, and 1 value per word. Okay, so we get queries, keys, and values. Okay, and then those are the ones that are passed on to decoder. Okay, and where do they enter the decoder? They enter the decoder via the encoder-decoder attention. Okay, so they enter here. Okay, so how does the decoder work? So let's actually look at this diagram. So if you look at the decoder, it's exactly the same except for this orange block here, right? Everything else is exactly the same. And by the way, last part of the decoder is that decoder produces some vector. Remember, it's the same issue with the RNNs. Produce some vector, but you have to map it back to, let's say, the vocabulary size, right? So you have a hidden, you have some, let's say, Z output. You have to come back to the number of, let's say, classes you have, right? So that's the linear layer and a softmax, okay? So that you can produce, let's say, a word. Okay. Now we're going to kind of understand on the decoder how is the decoder producing 1 word at a time. Okay, so in this diagram here, we're just showing that, hey, we got the 3 words, got embeddings with time signal, just means positional encoding. Passed to the encoder, we got three vectors, 1 for each word. Let's call it Z1, Z2, Z3. From those 3, we somehow got keys and values. Okay, so let's actually, we just get keys and values. Okay, forget about the queries I said earlier. So these 3 blue things from which we got this orange and this blue. Okay, so 2 sets of 2 keys and values. In fact, we can get multiple of them, but let's just focus on 1 of them. Okay. So we want to start talking about producing output decoded sentence. Could be a translation, could be an answer, could be, any output sequence, like a caption, whatever it is. Okay. So these keys and values will be used at every decoder level. Okay. So the same data will go to the first decoder, same data will go to the second decoder. Okay. So at time step 1, I want to decode, let's say I, right? So the first decoder output I'm not showing here is that first decoder output. Let's say we start with the start signal, okay, the start token. So I don't want to spend time on start token. So let's say I use the start token and somehow I got the first word. I want to now focus on like how do you get the second word, third word, and so on. Okay. So decoder self-attention. Remember, decoder is exactly the same as encoder, except for this encoder-decoder sublayer. So decoder self-attention, what they have to do is, because there is no other words, right? So while producing the second word, for example, I only know the first word. I don't know any other word, right? So self-attention, doesn't make sense, right? There's no other words. Or let's say I'm decoding the third word. I can only see the words before, but I can't see the words after. So the way to deal with it is basically ignore, there's no other word. So you can kind of ignore that part, which is set them to 0, or basically what is called mask the parts which are not yet there, okay, in the self-attention. Now, the decoder has the encoder-decoder attention, and that's where this keys and vectors, that's where whatever we computed from the encoder side is going to be used. So how is it going to be used is that let's say we got the first word I, then the I is, we get the word vector for word embedding for I, add positional encoding, pass it through the decoder's self-attention, and there's going to be encoder-decoder attention as well. In this diagram, I want to show how to, in this diagram, I'm just showing the decoding process. So I'm just showing that I is passed in, and it leads to am. I and am are passed in, it leads to A, and I am A is passed in, it leads to student, and so on. So here I'm not showing the operation of the encoder-decoder attention. Eventually, you get end of sentence and you stop. Okay. So, but how does the encoder-decoder attention work, right? So the mechanism by which, let's say we are trying to produce, let's say we're trying to produce the word student, right? So when you're trying to produce a student, we have 3 words that we've already decoded. So those 3 words go in, and we have to produce the next word, right? So these 3 words go in, and at the encoder-decoder attention level, these keys and values are multiplied with the z's to produce the keys are multiplied with the queries at the encoder-decoder layer to produce weights, and the weights are used to weigh the vectors, very similar to how we were doing it in the RNN case. It's just a weighted combination of the values, these values vectors, and then that is used along with the current vector to produce the output for each decoder unit. Okay. I don't want to show that operation because that just gets more messier than separately understanding what encoder-decoder attention is, which is what we did at the beginning of the lecture, and understanding what self-attention is, which is what we did with the transformer encoding unit. Okay, but just to say it here, those keys and values are going to be used while decoding, especially while decoding each next output. Okay, so we are doing it one at a time. So whatever word was produced here is going to be inputted here, and then while decoding, we're going to rely on the keys and values before to produce the next output. Okay. Any questions? Are you going to get, so there's a question, are we going to get sequential output from decoders if we don't use positional embedding and the encoder? Yeah, I mean, so if you don't use positional encoding and encoder, you will still get decoding process is always sequential. It's just that if you don't use the positional embedding, if you don't do this extra positional encoding, then positional information is not known to the network. And so it may not be able to rely on that information while producing the decoding. So it's as if you're just inputting a bag of words. I mean, of course, there's a lot more going on, but the word ordering may not, you will not be able to capture it because you're not passing it in. because there's no other place where you can say, hey, this is the first word and this is the second word. Self-attention is really symmetric. Okay, it just says, hey, this word just depends on everything else, but it doesn't say, hey, this word precedes that other word. That information has to be there somewhere. Okay, and that's because all the words are being processed at the same time, both in encoder and the decoder, but especially in encoder. It's very different from the RNN case where the first word is passed, first hidden vector is produced, second word is passed, second hidden vector is produced. So that is not going on here. RNN had the natural way of knowing that what precedes what. Here, that information is not passed in. And so you have to add positional information. But even if you don't add positional information, it'll still work. It's just that whatever is decoded is limited by training data. And so there's no explicitly, you're not giving information about ordering. So you'll still decode something. Okay. And maybe in some applications, the ordering doesn't matter and you can still use this architecture. Okay. If the input ordering doesn't matter, but you still need to decode sequentially, you can always use this architecture.
Thank you, Professor.
Professor, what will be the first input to our decoder? The very first input?
Oh, it'll be a start token, very similar to the RNN's decoder case.
Okay.
It's just that so decoder has a lot more complication going on because when we are computing these whatever outputs, much of the other vectors are not there, right? So that's why I mentioned there's the notion of masking, where you kind of ignore all the other computations because they don't exist. Okay, so it's like a little bit complex version of encoding where you don't care about like the second position, third position, fourth position, and so on, especially when you're doing forward pass in the first position. And encoder decoder attention, I didn't open it up too much because it's exactly the same mechanism as the attention slides that we saw at the beginning, but they just use keys and values from the encoder and queries from the decoder. Okay. So very similar to the decoder hidden state in the RNN case and the encoder hidden state in the RNN case. Those are getting multiplied. Here it's going to be keys and values and queries from the decoder side.
Okay.
Yeah, I think it's hard to wrap my head around the first time you're seeing it, but once you understand the building block encoder, I think decoder is not too complicated compared to that. And once you know that, it's just wiring of these blocks one after the other, very similar to how you have wired it in Keras or in PyTorch, right? So you just call layers one after the other. So in fact, there is an encoder layer in PyTorch implemented. You can just call it very similar to nn.embedding or nn.linear or whatever it is. Okay, so let me. So fine, I think we can just wrap up now. So just one comment is that whatever the decoder produces, it produces one thing at a time. That has to be transformed because you want to produce a distribution over words, and this is what is being shown here. So whatever vector you produce, that has to be linearly transformed to a distribution over words. Not just first you produce scores and then to a log transformation, you get probabilities, and then you just apply exactly, cross entropy loss. So you can see that, for example, let's say, if let's say my vocabulary is only 5 words or 6 words, then let's say the indices are 0, 1, 2, 3, 4, 5. Then you can see that, for example, my first output would be a 6-dimensional. You will encode if you encode a word like am with a one hot encoder vector like this, right? Am is encoded like this, or the word thanks will be exactly like this, except the fourth coordinate will be 1, and so on, right? So that's one hot encoding. And then whatever the model produces, model will produce 6 numbers. You just want to kind of compare with the location where the right word is. You just look at the log probability of that. I'm just explaining cross entropy loss by saying that, hey, where should be thanks be, and what is the probability with which you're saying thanks? Is that what is the score there? If the score is high, then your loss is low. If the score is low, then your loss is high. So that's just cross entropy loss. And here we're just looking at the cross entropy loss over all the 5 words that all the 5 words that you're producing. Am, I, thank, a student. Okay, so this is the definition of cross entropy. Okay, and you collect the cross entropy across all the words that you wanted to produce in your training data. So and pick up the right locations, and hopefully those locations have high values. Okay, then your loss is going to be low. So let me not explain cross entropy and confuse you more. It's just saying that once you get the softmax, so decoder will only produce a vector and that's like a hidden vector. So you have to do exactly what you're doing with the RNN case, which is you need to transform it back to the output space, which is the distribution over words in your vocabulary, and then do a cross entropy loss on that. Okay. So let me stop here, and if there are any questions, you can stay back and ask. We'll continue with an example next time, which is the use of BERT, which is a specific version of transformer for pre-training. Okay, it's pre-trained model that can be used for downstream natural language processing tasks. Okay, and we'll contrast it with word2vec as well as like pre-trained CNN models. So that's what we'll do next time, and then we'll get into some unsupervised learning ideas, and we'll see that next time. So thank you.